The question of the sequence in which blocks were installed in polygonal masonry has always intrigued researchers. Solving this question would provide additional insights into the construction order of polygonal structures. It would help identify the sections where construction began and aid in reconstructing its subsequent progress. This would make the logic of the process clearer. It would allow for certain conclusions to be drawn about logistics, and even about related aspects, such as the transformation of a raw piece into a fully finished block. Ultimately, this could lead to a more comprehensive understanding of the construction of these structures, their architecture, and, possibly, their functions. The question, as we can see, is significant. However, determining the laying sequence can be difficult, and often leads to serious discrepancies and debates. This is particularly true for masonry constructed from blocks of freeform shapes. By definition, the process of installing such blocks must have been more complex than laying cubic blocks. Sometimes, it is hard to believe that with such intricate surface configurations, it was possible to join them so flawlessly. After all, the connection had to be ensured not in just one plane but simultaneously in several. But what if the surfaces were intentionally curved? In this case, the task of achieving precise jointing becomes exponentially more difficult. All of this, both the tight fit of curved block surfaces and the intricate joint profiles, provides fertile ground for a wide variety of theories about how and with what tools this could have been achieved. One theory, for example, suggests that during installation, the blocks must have been in a plastic state. In this scenario, filling the voids between the adjoining blocks would not require additional effort. All the nuances of the curved configurations would be naturally formed. A malleable material would easily fill gaps with inconvenient shapes. As a result, the construction process would proceed without the difficulties that are inevitable when mechanically fitting blocks together. Such a method would also significantly alter the logistics of polygonal construction. The perimeters of the blocks would take shape not as a result of preliminary preparation but simply as a consequence of the installation process. However, this theory has several significant discrepancies with observed facts. There are no deformations that would correspond to the behavior of plastic materials. The natural structure of limestone, granite, and diorite, materials from which the blocks are made, remains intact. This alone casts doubt on the validity of the plastic theory and its various versions: clay-like, concrete, geopolymer. Another popular theory explains the tight joints of blocks in polygonal masonry by suggesting that their side surfaces were ground together using vibration. But here, too, modeling shows that the joint profiles produced by grinding would differ from those observed. Vibration would not allow for the creation of profiles that were so tightly joined along the entire perimeter of the connection. There would be excessive wear on the surfaces of the receiving profiles, leaving unfilled gaps at their edges. For example, in the case of placing a larger block on a smaller one, a corresponding wear pattern would form on the underside of the larger block. Protrusions on the raw blocks would leave indentations on the ground surface. Blocks installed over interblock seams would have protrusions underneath. But nothing of the sort is observed. With effort, it is possible to create matching surfaces using vibration. However, it is important to note that the volume of the raw blocks would decrease in the process. The result would be influenced by the mass of the blocks and the quality of their initial surface preparation. Most importantly, the process would only affect the ground areas of the surfaces. And this would be quite noticeable. All of this together makes such a method unsuitable, and its results do not match what is observed in reality. The traditional theory, which proposes the preparation of blocks using the pounding method, with simple stone tools, also does not provide complete answers. Jean-Pierre Protzen, an emeritus professor of architecture from Berkeley who studied ancient structures in South America, dedicated several books and articles to this issue. One of them, Inca Quarrying and Stonecutting, begins as follows. Studies of ancient quarry sites and numerous walls made of dressed stone show that the remarkable constructions of the Incas were created with very simple means. The fitting was achieved through a method of trial and error, by chiseling already installed stones. Smaller, half-kilogram hammers were used until the stone acquired the desired shape. Experiments show that using these methods, stone can be quarried, broken, dressed, and fitted without great effort and in a short time. There is quite a bit of confusion here. This includes equating ancient quarries with the Incas. This partly explains the categorical tone of the introduction. However, a few pages later, when discussing the results of his experiment, Protzen's tone becomes more restrained. The technology of fitting two stones is thus one of trial and error. I admit that this technique seems tedious and labor-intensive, especially when considering the Cyclopean blocks in Sacsayhuaman or Ollantaytambo. This is a remarkable acknowledgement of the difficulties associated with achieving a sufficient degree of monolithic structure in masonry. It is important to note that his experiment involved producing a stone with a relatively even surface and placing it on an equally flat surface, essentially imitating block-type masonry. There was no objective to create several blocks with complexly configured surfaces and then fit them together as precisely and tightly as was done in polygonal masonry. It should also be noted that to get the correct answer to his question, two stones with flat surfaces are not enough. It is better to experiment with 3 blocks. And the joining surfaces should be curved. Undoubtedly, this task is an order of magnitude more complex. To understand why this is so, we need to refer to the basic principles of the rule of receiving and responding profiles, which was covered in the second episode of the Traces of Alien Technologies series. The first principle is that masonry is created with several blocks, representing their connection. The second is that the blocks involved in the connection have receiving and responding sides. The third is that the curved surfaces of the mating blocks mutually match each other's configurations. All 3 of these principles are important to us. They take into account that part of the side surfaces of a polygonal block is the result of creating a responding profile, while the rest is the result of creating a receiving profile for the next block. The process itself is the installation of the block into a specially prepared receiving place. This place is located on at least 2, but often 3 or even 4 already installed blocks. In this way, through a kind of interlocking, additional fixation of the blocks is achieved, and the masonry as a whole is strengthened. Each step in the construction of the masonry was, therefore, both necessary and inevitable. Moreover, it left a trace in the form of joint profiles. If these are taken into account, the sequence of block installation is much easier to determine. For example, in this section, the second row could only have been laid in the following order. In this case, all blocks are installed without interference from neighboring blocks. The configuration of the responding part of each polygonal block mirrors the shape of the prepared receiving profile. Attempts to determine the sequence of laying polygonal blocks have been made repeatedly. One of the most well-known was made almost 40 years ago by Jean-Pierre Protzen. The laying scheme he proposed is based on considering wedge-shaped blocks and joints he calls horizontal and lateral seams. In our terminology, this is a type of receiving profile whose configuration resembles the letter L. If we analyze this section of masonry using the rule of receiving and responding profiles as a tool, Protzen's proposed scheme, largely correct, by the way, can be refined and supplemented with some details. He is correct when he says that block number 1 could not have been installed first. The builders had two options in this case. They could either install block 11 first, while there was still nothing obstructing it from the left, or wait until an obstacle appeared on the left and then try to fit a specially made block into the remaining space. It is obvious that the second option would require significant costs and efforts, without offering any visible advantages. Any builder in their right mind would prefer the first option. It is evident that blocks 7, 9, and 51 are in an equally difficult position. In fact, the laying order of the first row must have been as follows: 53, 52, 51, 9, 10, and then 50, followed by the 8th and 7th blocks. At the same time, the row on the left was being formed. First the large megalith, block 3, then blocks 4, 5, and the wedge-shaped block 6. Next, the corner was formed with blocks 2, 11, and finally 1. As a result, the first row was fully formed, and the corner megalith was installed. The second row was then formed, and its construction also progressed simultaneously from several points. In one of these points, construction started with block 57, followed by 56, 55, and 54. From there, the blocks were likely laid in several distinct groups. Moving to the left, the internal corner needed to be formed first. This involved laying block 19, followed by 20 and 21. Then blocks 17, 16, and 18. Next were blocks 13, 14, and 15. Finally, block 12 was placed. The third row was then constructed. Its construction could have proceeded from opposite ends, starting from the notches 60, 59, 34, 58, 33, 32, 31, 30, 35, 29. At the same time, filling proceeded from the leftmost megalith, 22, 23, 24, followed by 26, 25. In the end, two blocks remained, 27 and 28. The rule of receiving and responding profiles suggests that the final block in this section of the notches was block 28, and not 25, as might have appeared at first glance. Based on how the blocks were installed in this section and the fact that block 1 was essentially the starting block for the next section of masonry, it is indeed possible to say that construction in this sector progressed from right to left. However, in other sections, it could have moved from left to right. In the second and third levels of the notches, the blocks are smaller, allowing more flexibility in regulating the filling of rows, but the laying order is similar. At the same time, the outer blocks in the right part of the first level of the notches, as well as many blocks in its upper rows, have rough, clearly natural outlines on their exposed sides. This level, apparently, was not completed. It is possible that the upper rows were intended to be leveled or finished with another row of smaller blocks, similar to what was done in Tarawasi. But precisely what the ancient builders planned, we are unlikely ever to know. A slightly different picture is observed in Cusco. Apparently, the construction of the masonry here followed a somewhat different order. It began simultaneously from several starting points and expanded upward and outward from there. This is also confirmed by the fact that, alongside fully formed blocks, some blocks appear to be unfinished. Their receiving profiles were not fully formed or were absent altogether. This, in turn, raises questions about the methods and tools used to create them. Moreover, these blocks are not grouped compactly. They are not located in one section but rather at different ends of the structure. A similar approach is seen in Tarawasi. L-shaped joint profiles, which would allow for a clear determination of the block laying sequence, are also present here but much less frequently. The configuration of the blocks and their placement in the masonry suggest that this type of masonry relied on the targeted use of wedge-shaped sides of the blocks. It is somewhat like if a cubic block were laid not on its side but on one of its faces, into a bed formed by the sides of two other blocks placed in the same manner. This is, in essence, a slightly different approach to creating a seating place. It does not require the creation of special, receiving, recesses. The sides of already installed blocks effectively serve this purpose. Here, as in Cusco, the laying process moved upward and outward from the starting points. It could have begun simultaneously from several places, such as the corners of the structure and some points in between. In block masonry, the row pattern is maintained due to both the size and shape of the blocks. But even here, L-shaped joint profiles are regularly encountered. These, along with the curved side surfaces, contribute to better fixation of the masonry elements. Apparently, the preparation of blocks for honeycomb-type masonry must have differed from that of freeform blocks. It had more in common with the preparation of block-type masonry. In both types, certain requirements for block shape can be observed. For block masonry, these requirements are simply more specific. In both cases, the principle of block jointing in the masonry is similar. There is no regular need for specially created seating places, and this need becomes more occasional in both scenarios. However, in masonry with free-form blocks, specially prepared seating places were required by default. The reason was precisely the lack of any standards for the shape of the blocks. In the notches of Sacsayhuaman, there are sections with different types of masonry: free-form, honeycomb, and block types. It is clear that in free-form masonry, megaliths and very large blocks were regularly used. On the other hand, honeycomb and block type masonry consists of smaller blocks. Evidently, the laying scheme was determined by the size and shape of the blocks. Accordingly, this also dictated how the blocks would be joined. Here, we once again encounter a principle that is evident in everything related to polygonal complexes. Materials were used with the utmost consideration of their natural characteristics. All elements were integrated into their surroundings. Blocks were fitted tightly in the masonry. Complexes merged completely with the environment. This approach does not indicate limited capabilities or weakness on the part of the builders. On the contrary, such an approach could only be realized through a sufficient level of knowledge and a certain technological proficiency.